You all must be hungry by now. I hope you're not just hungry for food, but still also hungry for knowledge. We're going to take 40 minutes of your time, try to keep this exciting. So I work for a security lab. What we do is help our customers to make their products more secure by testing them. We provide test services, we provide test tools. Some of our customers come to us because they want to know how secure their product is. They are still in development and want to use our feedback to improve their products. Other customers come to us because they want to go to market. They're ready with their products and they just need to pass this final gate, certification. So those kind of customers typically don't like us to come back with a lot of issues because it will slow down their time to market. So we have to deal with these challenges. And when we do testing, it's important to realize that security testing is not the same as functional testing. In functional testing, typically you have a list of test requirements and you would be ticking your checkboxes with every test that you do. But security testing is a bit more creative. And I'd like to touch on the point, how do attackers work? So consider the amount of attacks that are possible like an apple tree. And there's apples everywhere. Now typically people that are looking for an apple would pick the low-hanging fruit. So every attacker would start looking for what is the easiest thing to do. But that is something that's not a constant. It's changing over time. So device security is actually a moving target. And as a security lab, we need to constantly refresh it, constantly change our methods, update it, make them smarter to help our customers to keep their products at a security level that's high enough. So when we look at the different sort of hardware attacks around, we classify them in 4 categories. There's invasive attacks. This is where we open up a chip, we put it under a microscope and we start reverse engineering the chip. We may find out the contents of the memory. Sometimes it's visible under a microscope. Sometimes we can put a probe needle on the chip to extract data running on the bus, or we can manipulate the data with this probe needle. Sometimes we need to go farther using a focused ion beam to make changes to the circuitry. These are very sophisticated attacks. They're typically very expensive. Often it's not the low-hanging fruit. In contrast, logical attacks are attacks where you're not doing anything physical. You just connect to the device and you try to communicate with it, try to penetrate from a logical point of view. These are attacks that are typically very cheap, but also systems try to be protected against them. It's not always easy to do that, so this could be the low-hanging fruit, but typically these apples are gone with a lot of systems that we see. Now then we have 2 more recent attack categories, fault attacks and sideshow attacks. Fault attacks are attacks where we try to manipulate a device. For instance, by using a laser beam, we open up the device, the chip, and we would hit a transistor with a laser beam and it would switch. So transistors are inherently sensitive to light, so we can do that. A little bit cheaper would be to overclock a device or to glitch the power supply. All of these methods are used to change the behavior of a chip to the advantage of the attacker. Side channel attacks look at information that is leaking from a device through the non-standard interfaces. To give an example of it, we're just coming out of winter in Holland. This picture was taken somewhere in winter, so I already see people laughing at this. So what's going on here?
He's growing cannabis.
So when I showed this slide a week ago, people said, well, there's probably somebody in there mining bitcoins. But you're quite right, there's a police car over there. And in fact, there's somebody growing weeds in the attic. So growing weeds requires a lot of light. Those bulbs are getting very warm. By that, the snow would melt. So this is a typical side channel case. Even though we cannot physically look inside the house right now, the snow is the melted snow is actually giving us a message. This is a side channel. When we try to do side channel analysis on electronic devices, this is typically the setup that we would have. We have a computer, we have a device that we're testing, we have an oscilloscope, and putting it all together we would get traces. Traces are observations of the power, the radiation, the energy used by a chip. So we start by sending commands to the device and getting back responses. And typically we would be interested in the cryptography. So we would be asking the device to encrypt some data, or we would be feeding it with a firmware update that's encrypted, and then the device starts decrypting it. But while it's doing that, the chip is radiating a bit of information, a bit of data, and we're capturing that with our oscilloscope, using a probe, and sending that back to the PC, which finally displays this in the form of a trace. So this trace represents the energy consumption over time. Now, how can we use this information to extract secrets? Let's have a look at this trace. So, anybody can see something special about this trace? It helps you a little bit. There's a variation of the interval between the dips. So you can see all these dips, and some of them are a little shorter and others are a little longer. So there's actually two variants there. Now, when I try to interpret those two variants with the green and the red dots, you can see there's an alternation of the green and the red marks, but it's not like always one green dot followed by a red mark. Anybody can guess what's going on here?
Square multiplier?
Right. So let me see some hands. Who of you is familiar with the RSA algorithm? Oh, that's quite a few. So what are the two basic operations in RSA? Square and multiply. So there's an alternation of two operations. Now, square is a special case of multiply, but if you implement it in hardware, typically you can make the square a little bit more efficient than the multiply. So this is actually what we're looking at. There's a square operation here, there's a multiply operation here. And how can we understand this graph? So this is a chip that includes a hardware accelerator. So the hardware accelerator does the modular multiplications. These are multiplications on large numbers, so typically 1,000, 2,000 bits. So while it's doing the multiplication, it is using a lot of energy. And at some point it's done, and then it goes back to the normal CPU. The normal CPU would move the data out, move new data in the registers of the accelerator, and start another multiplication. So these bits here are actually the changing of the processor between the accelerator, the crypto engine, and the normal CPU. So we are looking here at an alternation of square and multiply operations. Now in a basic implementation of RSA, every bit would take either one or two operations. It would take only a square operation if it's a 0. It would take a square and a multiply operation if it's a 1. So we can simply make this translation. So we can translate all those shorter and longer intervals into bits. And as a security analyst, we can now simply write down the key. So this is a very simple side channel case where with visual inspection you can actually extract a secret key. And this is what used to be possible up to, let's say, 10, 15 years ago. And after that, manufacturers started making this more and more difficult. But for sure, this was the low-hanging fruit in those days. So making a setup that can measure that is relatively easy, and extracting the key is a matter of minutes. So that was definitely the low-hanging fruit. There's no automation needed here. So things are changing now. So vendors are trying to reduce the signal and they're increasing noise. So it's becoming a hide and seek game. Yesterday when Francisco did his presentation, he talked about WDDL, he talked about masking. These are methods to reduce the signal. Typically the signal is not completely gone, but it's just getting less. Increasing noise is something that would happen when you deliberately start a process that makes a lot of transistor switching in a chip without having any specific activity related to that. It could also be parallel cores. So if an SoC would include several cores all running their own processes, it would generate a lot of noise. If the clock on a chip would be free running and it would not be quartz driven, but it would be free running, it would vary a lot over time. That creates timing noise. So nowadays, when we look at chips that have some level of protection against side channel attacks, we would see something like this. So it's very noisy. And at first sight, you might say, okay, very noisy, nothing to see anymore, so it's probably secure. Well, we're not ready for that conclusion. It's at least a little bit more secure because I cannot visually recognize any key anymore. But is it very secure? I really wouldn't be able to tell at this point. So I would start doing my side channel analysis, use filtering, all sort of techniques to increase the signal strength, reduce the noise. But it will take me quite a bit of time. I cannot estimate on beforehand whether this will take me 1 hour or 1 month. But this is something that I need to do as a test lab, because ultimately people will need assurance that a product is good enough, that this attack is no longer the low-hanging fruit. So we need to figure out a way to get that assurance, to measure the resistance of the device against this attack. So here's my challenge. Developers need to cover all bases, need to take away all the apples from the tree, but attackers need only one bug. So it's not really a fair match. When we do the testing, we provide assurance, but if these tests are inconclusive, then the assurance is actually missing. So we can only say, after a week of testing, we didn't find the key, but would we have found it if we would test it 1 day more, or would we need a year more of testing? So inconclusive test results are not really very nice. At the same time, we see the market demands fast and cheap testing. So with the introduction of IoT, new technology, there's no way people are going to wait for half a year before they introduce a product to market. It needs to go as fast as possible. So what we started thinking about 2 years ago was to apply deep learning. Deep learning is a technique that can do a lot for us. To make it possible to complete testing faster and get more assurance. So, what is deep learning? It is a technology that's based on neural networks, and neural networks have been around a bit longer. Deep learning typically uses more layers than neural networks did, let's say, 5 years ago. Deep learning is designed to be working with GPUs, so that means that hardware that's readily available to everybody can be used to accelerate deep learning. And deep learning is very strong on big data. So deep learning is applied a lot on the internet. I heard stories that Google and Facebook are able to recognize pictures of your loved ones quicker than you would be able to do that when looking at a web page. So this is really how strong these algorithms are. But they are trained on a lot of data. Now there's a similarity because in side channel analysis we typically also have a lot of data. So this got our interest. So when you look at Google Trends, you could see that people were discussing neural networks for a long time. But at some point of time here, I think in 2015, the term deep learning suddenly became more popular. A way of looking at the capabilities of deep learning is that the traditional learning algorithms would saturate quite soon. If you would be adding more data, the performance of the network would not go up, whereas deep learning has a curve that increases for a longer time. So adding more data will increase the performance this longer. This is related to deep learning being deeper, having more layers, and this is caused by breakthroughs in the deep learning algorithms that were developed about 10 years ago. The fun part is that there's a lot of frameworks available. You may have heard of TensorFlow, quite popular, but there's quite a few other frameworks. They are typically available, sometimes they're open source, sometimes they're just for free. So there's different solutions and people can play with it a lot. And we've decided to use one of those frameworks in our tooling. So we're not building, we're not designing, we're not implementing deep learning. We're just using deep learning as a library to enable side-channel analysis. So let's discuss a little bit how deep learning works. And I'm trying to use some analogies here that may help you understand what it does. So, for instance, if you try to recognize animals, you can use, my picture is not very clear here, but there's also dots here. So these are the color dots, but there's also gray dots in between. And these dots represent neurons. And every neuron is connected to neurons in the layer before. So there's several layers. There's an input layer here that's associated with the input data. And there's an output layer that's associated with what you might want to conclude. Now, just to imagine how this would work, here every neuron could be associated with one pixel in this picture. And these input neurons could just be looking at the color of the pixel. It could be all. Then there could be a second layer that would detect groups of pixels with the same color. There could be a third layer that is recognizing features like eyes typically have on the outside this one color, on the inside black. And the next layer could be bringing all the features together in order to guess which animal we're talking here about. Now, a second example, looking at a different animal, would basically be using the same network, but it would be activating different neurons. So the activation of the neurons is a result of the different inputs. And as you can see, every neuron is connected to the neurons in the layer before. The transfer of these signals are part of the learning process. So there's a weight factor for each of those transfer functions. And the learning process is actually going over training data over and over again and improving those weight factors until you reach a point where the results are best. So you're using the training data. Typically you would label them. So you would say this is a cat, that's a dog. And you would be looking at thousands of pictures. And the network is gradually training itself, becoming more and more capable, ultimately being able to make reasonable predictions of the animal we're looking at. Another interesting aspect here is this dog is nicely centered in the picture, but the cat is not. The cat is more to the left of the picture. Now, typically, neural networks are pretty good in solving these kind of misalignments. So whether the cat is left, on top, bottom, it wouldn't make much of a difference. So these networks are capable of dealing with that. Also, the shape of the head. Some cats might have bigger heads, smaller heads. The same animal, pictures of the same animal might be changing all the time. So this is what the neural networks are good at. In fact, there's a lot of neural networks. We've looked at quite a few of them, and ultimately we've chosen this type of neural network for a reason. So, a multiple layer perceptron would have an input layer where the size is equivalent to the number of features, and an output layer where the size is equivalent to the number of classes. And then it would have the hidden or dense layers in between that do the feature extraction. But a, for us, more useful solution is the convolutional neural network. It has layers in between that are very strong in feature extraction and solving the misalignment situation. So if the feature in the picture is left, right, top, bottom, this function here would be able to detect that. So it's solving the misalignment problem, which in side channel analysis is typically a problem that can be painful. So wherever the image is, the target is in the image, you should be able to detect that. Okay, so how does this translate to side channel analysis? Suppose we have a set of traces where there's a feature that is very interesting because it contains some confidential information. This feature here, I'm leaving out the noise, is for us to be able to recognize this. You can see it's shifted over time a little bit. So the CNN, the convolutional neural network, would extract the features and classify them. So tiny changes in those features could be related to different key values, if you will. So when you build a neural network, you have to think about hyperparameters. So these are the parameters that determine the neural network. First of all, there's the learning rate, the epochs, and the iterations. This is about the iterative process of the network of getting better and better. The regularization parameters is about preventing the network to be too much focused on the training data, or the slide on the later on. The activation function is about how each neuron would deal with all the inputs. So would it simply be a linear adder of all the inputs, or would it be a nonlinear? And if it would be nonlinear, what kind of function would be the output of the neuron? The number of neurons, how many do you use in parallel in one layer, and how many layers? There's a few more, but these are the more important parameters. And to detail a bit on that, so this is about the learning rates. If we are changing the weight factors of all the neuron interconnections with every step, we may be able to find minima, local minima, and a global minima. Now, with small steps, we might be able to find the global minimum. But if the step is too big, then we might actually jump over it without finding it. So big steps go fast, but you might miss the best configuration. So another way to represent that, if we have a low learning rate, it will take us a lot of time before we reach a low loss level, so a good quality. If we have a high learning rate, we're going to reach a low loss very early, but then we're going to stay at that level because we've missed the best position. A good learning rate would be a little bit slower, but ultimately it would arrive at the lowest loss. And obviously, if the learning rate is too high, then your loss will go quickly up because you're never going to find any of the minima. The problem of generalization or regularization, when we keep training our network on the training data, so we have a set of training data and we're running over the training data over and over and over again, so it's getting better and better, the error is going down. However, this network will be excellent in detecting the validation information, the training data, but not so good in recognizing testing data that you would be using later on. So there's a training phase where you make the network better and better, and there's an application phase or a testing phase where you're going to apply your trained network to new data. So this problem is called overfitting. The neural networks learn sufficiently from the training data, but they cannot generalize to new data. So the way to prevent that is by so-called early stopping. So there's ways to detect that the overfitting is happening and that this will be a problem during the testing phase. Okay, finally, some words about classification. So when we have as input a set of side channel phases, so all these dots here represent information or data over time related to the energy consumption of a chip. Any of those dots could relate to the intermediate data. So, let's say the state of a cryptographic algorithm. It could relate to the value of a key or anything else that has some sort of relation with the key. So what we could do, we could say, well, let's assume there's an intermediate value. It's a byte, and we assume that the amount of energy that is consumed will have a relationship with the Hamming weight of that byte. So that Hamming weight could be somewhere between 0 and 8. Then our network, after all, could be giving us the probabilities for each possible Hamming weight value. So here we have a set of probabilities that would add up to 1. We would say it's most likely that for this intermediate data byte, the Hamming weight was 6. Now, if we assume that that is true, the intermediate data byte has Hamming weight 6, it will tell us something about one key byte. It will tell us that that key byte may have a specific number of solutions, but not all solutions. So we would be reducing the entropy of a single key byte. And this is basically the way the attack works. So after applying the trained network to a smaller set of test traces, we will be assuming for every key byte first an entropy of 256 possibilities. And with every trace that we analyze, we see this entropy going down. It goes down from 256 down to 1. There's only one possibility that remains, and then we have found the correct value of that key byte. So this is the number of traces required to recover the correct key byte. Typically, you would like the training phase to be, you would allow it to be lengthy and elaborate and difficult, but you would like the application phase to be very fast. So let's look at the analysis flowchart. How does the process work? So as an attacker or as a test lab, you will start by acquiring a training test set based on a key that you know. And you would basically split that in a part used for the training and a part used for the validation. So the training process is changing the parameters, verifying that it works better than before, changing it again. If it works worse, then you're going to go the other way. So it's the training process uses the validation to verify that every new step was an improvement. This is very time-consuming. Training and validation, it's an alternation of two things. Then in a second phase, this is the test phase. This is where you would look at a trace set for which you don't know the key. So it's an unknown key. But now you're going to apply the trained network that you have. So the trained network is a model of reality. You apply that, and it is very fast. So what do we get from this process? We're going to get scores that tell us how good the keys that we're looking for are rated in the data that we're analyzing. During the training, we're getting to see the accuracy of the model, so you see the accuracy going up. You see the key ranking, so how is the entropy of the key going down after analyzing traces, and finally we extract the key. Now here I would like to do a small demo. Hopefully I'm not gonna suffer from the demo effect. So what we're looking here at is a set of traces. There's actually 10,000 traces recorded from a device that does the AES algorithm. It does an encryption. So you probably know that the AES includes 10 rounds, and here you can actually recognize those 10 rounds. There is a bit of noise here, but it is not a lot of noise. So this is not the most beneficial use case, but I want to do this demo in a few minutes. I don't want to take a whole week for that. So I'm using a set of traces that's not too hard, but it will show us how it works. So I'm going to do the training first. So the training is now starting, and this will take a couple of minutes. It's producing this kind of output that tells us something about the accuracy of the training. And it will process this key byte by key byte. So we're looking at AES, so that means that we are seeking the values of 60 key bytes. So it does this for 16 key bytes. For every key byte, we're running 20 so-called epochs. Epochs are repetitions in which you go over the total data set to try your new settings when applying the learning rates. While this is running, I'm going to go back to my next slide. So this is what we'll see in 2 minutes when we're finished. Deep learning can be compared to other methods being used in side channel analysis. So the method that was most popular 50 years ago was called CPA, correlation power analysis. And this graph shows how CPA manages to reduce the key entropy for each key byte. So again, starting at 256, it will take quite a few traces before you find the correct value, maybe up to 200. Then a big improvement was made with the so-called template analysis attacks. Dark blue and the green graphs, you can see here. And then the deep learning attacks came in. Oh, you can see them here. They are really very fast. So they don't need a lot of data to do the testing and extract the right key values. So this is something that we've measured using our own tooling. At this moment, we're working on a couple of improvements. We're trying to bring in GPUs. So the demo that I'm running here is only working on a CPU. My laptop doesn't have any GPUs, but GPUs definitely provide a lot of acceleration. In the experiments we've done so far, we can see that the training phase can be up to 30 times faster if you use a good graphical card. Another thing that we are realizing is that for difficult problems, the training phase can be very lengthy. So typically, the training is 100 to 1,000 times slower than the testing. So we're thinking about building databases using dedicated hardware, building these databases and trained networks that we can provide to our customers. So rather than having them to build these trained networks. We can train the networks for them. And just provide the trained networks and they can just apply. So my demo has not yet completely finished. So as I said, it's processing 16 keywords.
I have a quick question. If you
Yeah,
want
sure.
to earlier you said earlier you said that you would use the, yes, when you classify, you would use the Hamming weight per byte.
Yeah.
And my thought there was, why not use the value of the byte itself?
Yeah, yeah. That's a great question, and going back to my slide here, we're actually distinguishing that here. So this is deep learning on Hamming weight, and this is deep learning on ID. ID means the byte itself, and it's even stronger. So the red line here is the Hamming weight, ID is the blue line here, so it's even stronger. This is hardware specific. So for some hardware, we can be more successful using the byte values themselves. In some cases, it's very difficult to distinguish two bytes with a similar Hamming weight, and then we would just be looking at the Hamming weight. But potentially, this is an improvement. Can I postpone your question until I finish my demo? So here we see the entropy going down for the different key bytes. So there's some key bytes that are very soon at a low entropy. There's also some that need a bit more. This is also shown here. Let me see. Okay. Well, I can confirm here that the network is now able to recognize the trained data, but it's more convincing if we run this on another trace set. So now I'm going to run the test on a second trace set. So this is a much smaller trace set. It has, and we'll be using only a few hundred traces. Just to show you how fast the testing phase is. So this is the process for each key byte, and it's done already. So in just a matter of seconds, you see the entropy reduction. Yeah. So for those of you who can read it, key byte 1, 0, the correct key byte was found after 9 traces. For key byte 1, the correct value was found after 8 traces. There's a few that need a bit more. Here there's 60, there's 43, 37, but it's all very modest. Compared to the training sets where we used 5,000 traces. So this sort of demonstrates the capability of deep learning. Okay, I'm arriving at my takeaways here. So, yeah, attackers always go for the low-hanging fruits. As a lab, we try to provide assurance for product robustness by rating the resistance, so we should be able to measure it. And here we are pioneering deep learning methods and tools to seek maximal assurance for minimal effort. And that concludes my presentation. If you guys have questions?
Hi, thanks to you for both talk, it's interesting to see how you can be inventive creating distinction. But my question is, so you try to assess the security of the chips. And you say that the problem is that if you find nothing, you can deduce nothing. And to me, what seems annoying with machine learning when you try to do that is that, okay, you find nothing, you have no insurance that if you correctly selected the deeper parameters on your stuff, and I'm not sure that deep learning is really a good method for detections, maybe for attack, but to assess security of the chips, maybe not a good idea to tease effects.
Yes, thank you for your comments. So just to repeat it for everybody, you're acknowledging that if you as a tester do not find any proof that the product is bad, it doesn't necessarily mean that it's good. So it's only limited assurance. You can only say, well, I didn't find the key within a week time. So you would be looking for more assurance. We are trying to use deep learning here as a way to collect more assurance. But I think you're arguing here that if you don't know exactly how deep learning works, and you have not found, still haven't found the key after some time, you actually have more assurance. Is that correct?
It's not true. In the end, if deep learning didn't find anything, even if you try other methods, maybe that other methods that are more judicious will found something. Here, with the pure parameters, basically you add noise to your method.
Mm-hmm. Okay, so our view here is that this is just a stronger method than other methods that we have used before. So chances are that we will find more evidence than with other methods if we have a limited time frame. So there's, I guess, no magic in here, there's no silver bullet, it's just an improvement. This is a way for us to be more successful, to have a higher probability of getting the evidence that our customer is looking for.
Okay, any other questions?
Yeah.
Last one?
Just here.
Yeah.
So you mentioned that you prefer using CNN. I was wondering, do you build your CNN from scratch for your test, or do you rely on transfer learning, for instance, taking Google Net layers and then adapt yours to it?
We build them from scratch, so we're using a deep learning library. Mm-hmm. And we configure that with the data that we think makes sense. Some data is set by the example, like if you're analyzing AES and you're looking at Hamming weights, then you have 9 output neurons. If you're looking at identity, you have 256 output neurons. On the input side, you have 1 neuron for every sample that you're taking. So those are set by your environment, but there's still choice for how many layers are you choosing, how many intermediate neurons per layer, what's the learning rate, all those parameters. We are now in the process of finding out what's the best way of choosing those parameters. We're looking at genetic algorithms to help us do that quicker. It's a learning process for us as well.
One last question.
I was wondering if this approach will also be beneficial in looking for hardware trojans, or whether it's something you kind of consider.
It's an interesting question. So your question is, can we use deep learning for detecting hardware trojans, right? So we find that deep learning is good when there's a lot of data available. And we are not going to stop at side channel analysis. So we're also going to see how we can apply deep learning and other security testing techniques. For instance, we do a lot of source code reviews. Now, one of the earlier speakers talked about 10,000 lines of code. We sometimes get to review products with 1 million lines of code. So this is humanly almost impossible to do. So this is particularly a case where deep learning might add value. So yes, we will be porting deep learning to other security testing domains. Whether it will be useful for your application, I cannot answer that yet, but I think the key here is can we collect a lot of training data, because that will make it easier.
So we're actually looking at this as part of one of the projects in RISE. Exactly what we're talking about. So we can talk about later. Okay, I'll have to leave it at that. I think you're joining us for another
Yeah,
while.
so I'm available for lunch. Can I, one final thing? A bit of advertisement. We're looking for good people to help us move further. Not just people that want to work for us, but also interns, people that like to do new inventions with us, research this material. So I'm happy to talk to you.
Okay, so if you have any further questions, please contact Mark over lunch. And let's thank the speaker again.
Okay, thank you.